All right, this one's for 4th hour physics. We have our little copper cannon that's firing a little bullet at 40 degrees. Its initial velocity, we said, I believe, was 5.6 meters per second. I want to know how far downrange this little bullet's going to go. If you look at a problem right here, as soon as you see something on the, not on the X and Y axis like that, just get rid of it. It's got to go. So let's break this into its component parts. This will be hypotenuse sine theta, which is the same thing as saying 5.6 meters per second times cosine of 40 degrees. And if you put that in your calculator, you land up with 3.6 meters per second. And down here, we're going to have hypotenuse cosine theta, which is, again, 5.6 meters per second. That's the hypotenuse. Cosine of 40 degrees. And if you put that in your calculator, you land up with 4.3 meters per second. All right, we broke this vector into its component parts. You don't need it anymore. It's gone. So you can describe the motion of this bullet as going 3.6 meters per second upward, and at the same time going 4.3 meters per second down towards the eastern side, if you want to, the positive x direction. So you don't need the other vector. I always encourage, scribble it out, erase it, get rid of it. This describes the motion of the bullet. Now, the first thing we know is that gravity dictates how long the bullet will stay in the air. Think about it. If you're in outer space and there's no gravity, you're out in deep space somewhere between the galaxies, and you fire a bullet, it will stay in the air forever. So it has nothing to do with gravity at all. But here on Earth, if it's moving straight up with a velocity of 3.6 meters per second, we can use one of these y-directed formulas to help us solve how long it's going to be in the air for. So let's look at our choices. This is a cliff formula. Y is equal to 1/2 at squared. Will that tell us how long the bullet's going to be in the air? No, this is the cliff formula. It's for things falling off a cliff. Is this falling off a cliff? No, it's being shot upward. Can't use it. That is specifically for things falling off the cliff. It's really this formula. Can we use this formula? Do we know the Y final? The bullet goes up and it comes down. It lands at 0. Yes. Do we know the Y initial? Yes. It's fired from the 0 mark in the Y direction and it comes down. Sure, we know that. Do we know the velocity initial? 3.6 meters per second. Do we know the time? No, we don't. Do we know acceleration? Yes, we do. Can we figure out time squared and time? Yes, we can using the quadratic equation. So this works. Got to use the quadratic. Let's find something simpler. How about y final is equal to y final squared is equal to, let's try that again. Velocity final squared is equal to velocity initial squared plus 2ay. It doesn't say anything about time, so we don't want to use that equation. Let's look at this equation. If you fire something upward, velocity final is equal to velocity final is equal to velocity initial plus at. Do we have a velocity final if we fire something up? Yeah. If we analyze it just for half the motion, if we analyze it for the puck going up, what's going to be the velocity at the top? Velocity is going to be 0. So, okay, velocity final, we'll take it at 0. We'll just look at half the motion. Do we have the velocity initial, 3.6? Do we have the acceleration due to gravity, -9.8? Can we determine time? Yes, that's a great formula to use. So let's look how long this is going to be in the air for. Velocity final is equal to velocity initial plus at. Right? We don't know t, we know everything else. So velocity final minus velocity initial is equal to a times t. Divide each side by a. And this will tell us how long the puck will be from the ground to the air, to the top. And then just double that, because from the top to the bottom, it's going to take the same amount of time. So if I throw this pencil up, and it took 0.5 seconds to go up, it's going to take 0.5 seconds to go down. That's something that you're going to exploit all the time. So when we put the numbers in, velocity final is 0. Velocity initial, we said, was 3.6. Over acceleration, which would be -9.8 per second squared. how long it's going to be in the air if it's going up and stopping at its peak. So we have to add twice that amount to get it to come back down. So multiply this by 2, and our time is equal to 0.73 seconds. That's how long the bullet is going to be in the air, the cannonball is going to be in the air, which is going to go up and back down 7.3 seconds. Big question is now, how far downrange is it going to go? Well, we have to use the x-directed formulas, and the only formula we have, velocity is equal to distance over time. So let's look. Do we have the velocity? Yes, we do. 1.3. Do we have the distance? No. Do we have the time that it's in the air? Yes. Can we calculate the distance? Distance is equal to velocity times time. Velocity is 4.3. Time is 0.73. We will get 3.1 meters seconds canceled. So this is how far a bullet will go. Now we're going to try this tomorrow in class. We're going to take the copper cannon. I know it's, I believe, once again, we'll test it again, but I think it's like 5.6 meters per second. That's the speed. We'll aim it at 40 degrees, and it should land up 3.1 meters downrange. In other words, got the cannon, it's going to go up, it's come back down. This should be 3.1 meters. That's how you do that problem. If you don't know how to do it, you're going to do a lot more of them with a lot more explanations. It's going to be the same explanation, the same problem. You do it 10 times, you'll get it.